Hello, my name is Jawad Ahmed Fareed, and in today's session, we will walk through the process required to calculate value at risk for currencies and commodities. When we close this session, we will also take a look at how the VaR process applies to calculation of value at risk for fixed income securities and bonds. In today's session, we start off with a simple data set for a handful of currencies. So if you see the sheet over here, you can see we have rates for the European Union currency, the euro, the Australian dollar, the Japanese yen, and the British pound. And side by side with that, we have three energy commodities, so Brent, WTI, and natural gas, gold, and silver. By the time we are done with our session, we would have calculated value at risk for all 1, 2, 3, 4, 5, 6, 7, 8, 9 securities. We would have calculated value at risk for a portfolio of these securities, and we would have done this using two primary approaches: the historical simulation approach and the variance covariance approach. In a more advanced session, we will look at how this methodology can be extended and how this compares with the results generated by a number of additional techniques. Alright, so now to start off with, we have the sheet in front of us with the data. What I want you to do is to simply add two columns to each of these areas. So I'll go ahead and add insert. I'll add and press Ctrl Y. So that adds two columns against the euro. I'm going to go ahead and repeat this process for the Australian dollar, and then the Japanese yen, and then the British pound. Right? And then let's do the same thing with Brent, WTI, natural gas, gold, and silver. Control Y to get me two columns. Then the same thing for, Control Y for WTI, and then for natural gas, and then for gold. Alright, so now we've added these two columns. The reason why we've added these two columns is I'm going to track two areas. In the first column over here, I will actually calculate what we call the daily return series. So let's just call this daily returns. This is my daily return series, and then on this side I'm going to calculate what I call trailing vol. And when we review this, when we build this sheet, we will see exactly how these numbers are calculated and what do they mean. I'm simply copying and pasting the headings so that we have the sheet ready. There we go. Now, if you remember in the PowerPoint presentation, we'd spoken how the return series is calculated. Within the value at risk framework, we calculate return series by simply doing ln P1 over P0. This value here is P1, this value here is P0. So a simple formula for ln, which is the natural log of P1 divided by P0. And this gives us a return of 0.003762, which is the rate of change in the price of euro as on 4th of January 2010 compared to 2nd of January 2010. All I now need to do is simply copy and paste this cell all the way to the bottom. As you can see, when we go down, we'll see data up to 19th August 2010. So we have about 8 months worth of information in total, which is about 180 plus minus a few days worth of data. So press Shift Insert, and I now have copied this entire series. So this is my daily return series. Let's go out and replicate the series for all the other currencies in our portfolio. So let's do Control Insert, Shift Insert for the Australian dollar, Shift Insert for the Japanese yen, and Shift Insert for the British pound. So now that we've done this, we need to create some space for us to store the results that we are going to calculate. I'm going to simply add a few rows on top so that we have space to work and play. Now, for the calculation of standard deviation or volatility, let's start with the simplest approach. And the simplest approach is to simply calculate STDEV, or the standard deviation function in Excel, and apply that to the series, this results over here. And this gives us what we call our estimate for daily volatility. So this is daily vol. Daily volatility for the euro is 0.007411. How does that translate into annualized volatility? Annualized volatility is simply daily vol times the square root of the number of days involved or required as far as this calculation is concerned. So let's make an assumption. Let's make an assumption that the number of days in a year are 260, which means that the annualized volatility for the euro is going to be the daily vol times the square root of 260. And let's plug that in, and there we go. So the daily volatility, so the annual volatility, the annualized volatility for the euro as per this series is just about 12%, 11.95%, and this is so about 70 basis points per day and about 12% a year. Now, if this is the number for the euro, what does this number look like for the Australian dollar? The same two numbers for the Australian dollars are. So we need to, before we copy it, we need to make sure that we lock and anchor this cell by pressing F4. When we press F4, we get two dollar signs. The dollar signs lock in the row as well as the column. So if I copy and paste this again, I can see that the annualized volatility for the Australian dollar is about 14.9%, and the same volatility on a daily basis is about 0.9% or 90 basis points. For the Japanese yen, it's about 9.85%. For the British pound, it's about 11.64%. So as per this data, it's the Australian dollar which is the most volatile, followed by the euro, followed by the pound, followed by the yen. So the number that you see in front of you here, 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 and here is the annualized volatility number calculated using the entire data set of 8 months of data. If we have more information, we would simply extend this process to get an idea of what the standard volatility or the analyzed volatility looks like. However, before we move on, there is one quick check or one quick trace that we should add, and that trace is what is the maximum volatility that you're likely to see, let's say over a 10-day period. Now to do that, I need to calculate what I call trailing volatility, and when I look at trailing volatility, all I'm going to do is I'm going to take this set of returns, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's say 11. So I'm going to take 11 days worth of returns, and I'm going to calculate the volatility for these 11 days, and then I'm simply going to extend that volatility in such a fashion that for every day, so st dev of this series for, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 10 days worth of data. So this is the daily volatility for these 10 days worth of data in early January. If I cut and paste and extend this series all the way down till here, you will see that this number moves around quite a lot. And if I were to simply turn this into a percentage, what I'm really seeing is that if I were to calculate the minimum and maximum values of this series, minimum and maximum values, the minimum trailing volatility that you are likely to see or experience is the min of the trailing vol series here, which is which is about a third of the number that we've seen here, and the maximum number that you're likely to see, again based on this data set, is almost double the number. So what we're really saying is that volatility moves around quite a bit as far as if we use a measure of volatility like trailing volatility. To better illustrate this, it would be useful to convert this series into what we call a graph or a plot. So I'm going to select this data set here, and I'm going to go to insert, then click on a line graph, press line graph, and there's my series. And I'll simply move it, so cut this take it all the way to the tops where we can see it in accordance with everybody else, and simply paste it. So paste. There we go. So now a, I have a series. Let's label it properly. Let's label it change select data, and let's call the series this is the euro or EUR. Go back to our graph at the top. There we go. So now we're saying, as far as the euro is concerned, the range of numbers that we've seen over, let's say, 170 days, on the low end we've seen about 0.5%, on the high end we've seen about 1.5%, and there have been a few instances where it's actually gone as low as 0.28%. If we repeat this process, the same calculation that we've done here, if we repeat this process for our friend the Australian dollar, the Japanese yen, and the British pound, we will see some interesting results. So let me just select this, control insert, and then paste it for the next three currencies, for the Australian dollar, for the Japanese yen, and for the British pound. And since I'm at it, let me also add these three to the plot. So let's make some more space so that we can play with 1, 2, 3, 4, 5, 6. This is more space. Let's select the chart, go to design, select data, add the new series. Let's call this series, the second series is AUD, the second series is around here. There we go, that's the second series. Okay, add the third, which is add third. Let's call this JPY, which is available here. That's Australian dollar. There is JPY. Click and press OK, and then add the last one, which is the British pound. Let's call this GBP. Select the data, and the British pound, our friend the British pound, is available here. Alright, so what we've just done is we've gone out and added these three series to our graphs just to see how does volatility behave over a period of time. And as you can see, what you're really seeing here is the volatility tracked on a 10-day basis, on a 10-day trailing basis, on a 10-day backward looking basis. And the parts that I'd like to highlight and identify here is that if you look at this from a vol point of view, we can see that the yen is possibly the most stable of all of these currencies, shuttling between, if I were to simply take the min and max calculation one more time and copy and paste it here so that we have similar analogs and numbers for our calculations for the other four currencies, you can see that for the euro the range was 0.28 to 1.59, for the Australian dollar is 0.32 to 0.02, for the yen it's only 0.26 to 1.0, and for the pound it's 0.3 to 1.6. This is where the Australian dollar really breaks out. We don't have the exact date, but we're saying if you start on early January, 120 days later, this is the time, this is the crisis time at which all currencies really spike. Anyhow, so the idea is if you're building a value at risk measure that is linked to volatility, a trend like this creates some interesting questions. As long as you stay within this range, even though this range is quite volatile, a trend like this creates some very interesting questions. How does VaR behave and move over a period of time? Once we've calculated the VaR numbers, we'll have another opportunity to revisit this question. For now, let's go out and see how do we calculate value at risk now that we are armed with an estimate of both daily and annualized volatility. So for VaR calculation purposes, if we start with the very first approach, which is the variance covariance approach, we first need to agree on a confidence level or a confidence interval, and I will simply call that CI or the for confidence level. Let's say I'm looking at 99. Maybe it would be useful to put it. So let's remove this graph, put this on the side. Let's say the CI is at 99.9 percentile, which means that the Z factor or the multiplier factor, the multiplier factor is simply norm S INV into the probability of CI. There we go. So we're saying at 99.9 percentile, the multiplier factor using the normal standard distribution. So this norm S stands for standard, norm SINV stands for the inverse normal. So what we're saying is, if I give you a confidence level of 99.9, what's the corresponding Z-score that I need to work with? The Z-score is 3.09. So if I'm calculating the value at risk on a daily basis, let's say the holding period here. Now the holding period as per the Basel document or the Basel II document is 10 days. In this specific instance, we're saying the daily volatility is 0.74, so a movement in my numbers on a daily basis is 0.74. If I use a holding period of 10 days, since I'm not using space, let's just use this here. If I'm using a holding period of 10 days for my position, then the value at risk calculation is simply going to be the daily volatility scaled for the holding period. So the holding period vol is simply the daily vol, this number here, into square root of the holding period. So the holding period volatility is about 2.3%. And what's the value at risk using the variance covariance approach? The value at risk using the variance covariance approach in percentile terms is this factor, the multiplier factor at 99.9 percentile, 3.09, into the holding period vol, which is this number here. So the worst case movement that you're likely to see over a 10-day period using value at risk is about 7.2%. And this is using the variance covariance approach. Now, how does this compare with the number that we've seen here? What you're really saying is that, look, if VaR ever, what's the most that the Australian dollar could move in a given amount of time? I think the worst case number that we have for an average of trailing volatility is about 1.59. If I simply take this maximum estimate of trailing volatility and do a crude approximation on this, I'm saying the maximum trailing vol I've seen is 1.59 into the square root of the holding period, which is here. The number that I get is about 5%. Right? But remember, this is based on the assumption that the maximum value that we're seeing over a 10-day, the worst case move that we're likely to see using an average of trailing volatility, using an average of 10-day vol is 5.01. If I reduce this to, let's say, 5 days or 3 days or 2 days, then this number will move around quite a bit. So what have we learned so far? What we've learned is, in terms of the sequence of actions that are required to calculate volatility, our first step was to work with the data set. Second step was to calculate daily returns, which we just did. Our third step was to calculate an estimate of daily volatility, which we did over here. Our fourth step, which is not necessary for the actual calculation of value at risk, but is useful for interpreting the results that we see, was to calculate what we call trailing volatility. Volatility based on a 10-day data set, and trailing in the sense that you repeat this calculation all across so that you have a path and a trend that you can work off with. Once we had the daily volatility, we worked with a holding period or estimate for holding period, which in our case was 10. We also agreed on a confidence level, and that confidence level or confidence interval was set at 99.9 percentile, which basically means that there's only a 0.1% chance that you are going to see, that you're likely to see a move of more than 7.2%. Now, just as a quick cross check, we picked our maximum value, the maximum value that we're likely to see when it comes to the holding period of 1.59. We multiplied that by the square root of 10 to find out our crude approximation for the worst case move, and that worst case move is of 5%, which is not that far off from 7% shock. If you reduce this to 99 percentile, what happens then? If you reduce this 99 percentile, you see that the factor, the multiplier comes down to 2.32. Your VaR estimate also comes down to 5.5. You reduce this a little further from 99.9 percentile to, let's say, 97.5 percentile. So there's a 2.5%. You find that your crude shock is actually higher than value at risk. So what's really happening here is that as you play with the multiplier, as you play with the confidence level, you see VaR going up or coming down. The crude, the maximum number that we've had here, the crude approximation we put in here, 5.01, however, works off the peak of volatility, which in the case of the euro is somewhere about here. And you're saying, what's the worst case likely movement that I've actually seen in the past? The worst case likely movement that I've seen in the past using this number, using this range is about 1.59. 1.59 times the square root of 3 gives us 5.1. So I hope this sort of helps you understand and clarify the actual process for calculating value at risk. Now that we have these numbers, let's go out and calculate, then repeat this calculation for the other three currencies. I just need to make sure that I've locked in. Yeah, this is fine. Let's just Control Insert and copy and paste these for our friend the Australian dollar. The VaR number is off because most likely because I haven't locked in an appropriate cell. B16, yep. So I just need to make sure that our cell B3 is locked, F4 is locked. Square root of 7, this is fine. 10 is fine, and this is also fine. So if I now repeat this again one more time, that's the Australian dollar, that's the Japanese yen, and that's our friend the British pound. Okay. So once again, now what we're saying is that the numbers that we want to focus and highlight on are here: 4.6% for the euro value at risk, 5.7% for the Australian dollar, 3.8% for Japanese yen, and 4.5% for the British pound. Now, value at risk traditionally, conventionally is always represented and viewed and presented as an absolute number or in a dollar amount. We've used percentiles because we don't have a notional amount as yet, and we just wanted to work with an approximation to see what kind of numbers we likely to see. Now, the interesting thing that you should see is that at 97.5%, at 97.5%, using 97.5% as the confidence level, the VaR numbers, the actual VaR numbers, are all, the only instance where there is an exception is in the case of the yen, where the crude VaR number is actually less and lower than 3.8, and the actual number for both the pound, the dollar, the Australian dollar, and the euro are actually high. Now, what does this tell us? What this tells you is that there is a very interesting disconnect, and to look at that disconnect, we actually have to evaluate and work with the second method for calculating value at risk, which is historical simulation. So we'll use the same data set. All the work that we've done will get reused. The only difference in how is this calculated. So our next step, now that we have an estimate for value at risk, and let's clarify this. This is value at risk using the variance VCV approach or the variance covariance approach, which assumes normality of returns. Let's say what happens if we need to calculate value at risk using the historical simulation approach. Now, for the historical simulation approach, first let's look at how many data points do we have. So total number of data points that we have is simply a count of our return series. So we have about 181 data points. Now these 181 data points, let's move it here because we're not going to use it elsewhere. These 181 data points, if I were to ask you what is the worst case possible loss, the worst case possible loss is simply the minimum return that you've seen. So this is max vol and this is min vol. and now we're talking about minimum return. The minimum return that you've seen in a given day using this data set as your base is simply the minimum of the daily return series here. Yeah, there's your return series, right? So that's your minimum. So your minimum return is 0.2768, and this is the minimum return over a given day. If I simply reduce my holding period to 1, there we go. Now, so now what I'm saying is, I'm saying my minimum return is in a given day over these 181 days is minus 2.7%. And if I repeat this calculation for the Australian dollar, it's minus 4%. For the Japanese yen, 1.96%, and for the British pound, it's about 3.04%. What does this minimum number represent? This minimum number represents, for all four currencies, the worst possible loss that was realized, that was seen, that was observed in the last 181 days. If you invert this, what you're saying is my actual probability that corresponds to this loss is 1 over 181, or 0.005525. If I do 1 minus this number, I'm saying there is only a 0.55% chance that I'll see a loss greater than this amount, right? If I tweak my VaR model by the same amount, I'm saying the worst case loss is 99.45. What is the worst case loss that corresponds to this number? You've seen that this number changes, the multiplier has changed, and so have my value at risk estimates. So the two numbers that I want to compare, that I want to highlight, that I want you to see and observe are here. Let's put a different color. Yeah, let's just do this. And that's too dark. Let's do a lighter shade. There we go. So that's one number, and then we have another number which is here, which is our VCV approach. So now this minimum return is his actual realized historical return. And this actual realized historical return basically says that while a VaR number in percentage terms is 1.9% using VCV, the actual worst case number corresponding to the same confidence level is minus 2.77. While a worst number using variance covariance approach for the Australian dollar is 7.4, the actual realized number is minus 4.0. For the Japanese yen, the risk number is 4.9, the actual number is 1.96. For GBP, the VCV number is 5.8, the actual number is 3.04. So which one of these numbers are right? To answer this question, I think you have to take the data that you have and build a histogram. So before we build the histogram, let's just make sure that all of you have, if you click on your data tab in Excel, have this under analysis. So this is data analysis tools. If you can't see this, if you can't see data analysis or solver or what if analysis on this side, all you need to do is go to Excel, click on Excel options, click on add-ins. When you go to add-ins, you will see list of active add-ins, list of inactive application add-ins, and in the bottom you will see something called manage Excel add-ins. If you press go here, you will see you have the chance to add. So analysis toolpack, VBA, conditional sum wizard, and solver add-in. Please make sure that these are ticked. When you press OK, Excel will install these elements if you already don't have them on your worksheet. Right. So now my assumption is you've taken you've taken a few minutes to make sure that you have this. If you don't have it, you've installed this, and we can now move on. Now to what we're going to do next is we want to, just like we've seen this in a graphical context, we want to see how does this look, where does this 2.77 come from, and how does it correspond to this 1.9% number that we see here, and what does this tell us about the relative merits or demerits of the variance covariance approach versus the minimum return or the historical simulation approach. Right. So what we do is we say, give me the daily returns here click on data analysis, click on histogram, press OK. For the data set, use this series that I've already highlighted, and then use a new worksheet, give me a cumulative percentage and give me a chart output, and press OK. So if you press OK, Excel simply goes out, open the new sheet. In that specific sheet, it goes out and calculates the histogram. And let's label the sheet. Let's call this Euro Hist for Euro histogram. Okay. Now, to clean this up, let's put some percentages here. There we go. So what is this graph showing? What this graph is showing us is it's showing us a couple of things. First of all, this histogram is showing you how, so there are two pieces, you have a tabular breakdown here, right over here, and at the same time you also have a graphical breakdown which is over here. So what this graph is showing you is that in the entire history of how many days? We had 181 days, so let's look at 181 days, sum of the series. In the entire history that we have in front of us of those 181 days, there was only one day where the euro lost more than 2.77%, and the probability of that event is 0.55. There was another day, there were 2 days when the euro lost 1 and 2, where the euro lost more than 1.97%. There were 5 days where euro lost more than 1.58%. So you can simplify this by simply calculating sum and then this plus this here, and then so that's your series. And if you want to look at probabilities, if you want to look at where do these numbers come from, all you need to do is simply take this 1 and divide it by 181 here. Press F4, there we go. This is the same percentage, the same probability that you see on this side. Alright, so that's 0.55. Scroll it down and you have 100%. So what this table tells you is that for a given confidence level, what's the appropriate threshold? What's the appropriate threshold for the worst case loss? At 99.45%, it's 2.77. At 98.9%, which is 1 minus 1.11, it's 1.97. At 85%, it's minus 0.78. At 70%, it's about 0.39. Right? So this gives you a fair idea of what numbers you see. Now over here, you have the same information represented in a graphical form. And this line here shows you the cumulative distribution. So what you're saying is, look, if I'm interested in if I were to extend this and prove it, you're saying my worst case loss is about here. So I have a loss here and a loss here. My worst case loss is 2.77. The next worst case is 1.97. The third worst case is 1.58%, and then 1.18%. And the range of results, the range of values that you see here, give you a fair indication of how it's distributed. Now for the euro, the interesting piece is that what you're saying, if you go back to the actual calculation, for the euro you're saying that the actual distribution, the realized historical distribution, actually has a fatter tail than the normal distribution. Because if it was thinner, if it was before the normal distribution, the number that we see here would be 1.79. Sorry, 1.9, the number that we see here, not 2.77. And because it has 2.77, this is an indication that as far as we are concerned, this distribution is actually a little different from the normal distribution. We can see that, and its tails on this side are actually fatter than the normal distribution. If you repeat this calculation, we repeat the same exercise, so we build one histogram for euro. Let's build the same histograms for our friends, the Australian dollar, Japanese yen, and the British pound. So data analysis, let's press histogram. Our data for the Australian dollar is in column G. So let's simply replace this by G, or is it G, or yeah, no, it's not G, it's actually F. So let's replace it by F and press OK. So that's the histogram for Australian dollar, and repeat this for one more histogram. Let's make this, sorry, two more histograms. Let's make another histogram for our friend the Japanese yen. The Japanese yen is here. This is the return series for the Japanese yen, which is in column I. So I simply update the cell. You actually go and select the cells also, but I prefer doing it this way. There you go. That's the yen histogram. And then finally, the last and final one is the British pound. So you come here, you press the British pound is here in column L. So we replace I by L, place I by L, you press OK, and we have all three. Now, a little bit of formatting. So update this. So this becomes the British pound, GBP, history. Little bit of formatting on this side to make the graphs more representative and presentable by simply converting the first column A into a percentage. Same thing for our friend here, the Japanese yen, becomes more readable, and for the Australian dollar, so that it becomes more readable. Okay. Now, one of the things I want to do is I want to simply cut all of this, put all of these on one sheet so that we can compare. We did the euro here, so let's just put this here. There we go. That's our friend the Australian dollar. That's our friend. Let's copy this, copy and paste it here. Paste. That's our friend the euro. So same scale, just so that we can see how things or how widely distributed the distribution is. Shrink it a bit. Okay. So now what you're doing is you're comparing the euro with the Australian dollar. The one on the bottom is euro, the one above is the Australian dollar. Bring it closer. There we go. So now if you see, the first thing you can see is that look at the range. This goes from -4 to 2.8 plus. This goes from -2.7 to 1.99. They look normal from a distribution point of view. It feels as if they're normal, but you can see that the Australian dollar is actually quite skewed on this side, and the euro is actually a little peaked on this front in the middle. And other than that, the range is also out, right? And the same thing that you see here, same calculation we did earlier, there is only a 0.5% chance that you will see a loss of more than 4%. So what we're really doing here is we've calculated the volatility and the value at risk using the variance covariance approach, which assumes that the underlying distribution is normal. In our second step, we actually use the inbuilt Excel function of a histogram to calculate volatility for our four currencies. Calculate the worst case loss for our four currencies using the Excel histogram function to get an idea of what does the actual true underlying distribution look like. If I were to simply copy all four to this sheet where we've dumped all the other results, so edit, paste. Go, and finally this was the yen, and this is the British pound. Copy and paste and paste. So we have this, and if I just reduce the size so that we can see all four, need to do a little bit of adjustment. So bear with me for a second. That's number one. So the sequence, if you remember correctly, it's the euro on top, followed by the dollar, followed by the Australian dollar, followed by the yen, followed by the British pound. So now we have all four on one page, one little notch, and yeah, there we go. So now we have all four on one page. and this is our friend euro. This is our friend the Australian dollar. This is our friend the Japanese yen, and this is the British pound. Now, if I were to calculate um, value at risk using historical simulation, all I need to do is pick this number. That's the number I want. That's the worst case loss. The worst case loss for euro, the worst case loss for Australian dollar, the worst case loss for JPY, the worst case loss for the British pound. And for historical simulation, this worst case loss corresponds to the inverse of the number of data elements, which as we've seen earlier were 181, which means that if you have only one entry or one entrant in this case for all four currencies, for euro, for Australian dollar, for the Japanese yen, and for the British pound, that one number corresponds to the worst case loss that you're likely to see with this level of confidence. There's only a 0.55% chance, only a half a percent chance that you will see a loss greater than 4% over the next one trading day when it comes to the this is the Australian dollar, my mistake. This is the Australian dollar, this is the euro. So there's only a half a percent chance that you're going to see a loss of greater than 4% over the next trading day for the Australian dollar, a loss of 2.7% for the euro, a loss of 1.96% for the yen, and a loss of more than 3% or less than 3% for the British pound. So the primary comparison, the benchmarks that you need to see, if this is right, the benchmarks that you need to see are here. If you put these side by side, you're saying my VaR number is 1.9, my historical simulation number is 2.7, my VaR number is 7.4, my historical simulation number is -4, my VaR number is 4.9, my actual realized number is 1.96, my VaR number is 5.8, actual number is a little different. If the minus sign confuses you, you can simply put them in here and the minus sign goes away, and if that was causing confusion, it should no longer cause confusion. So now point I want to highlight is for the euro, the realized distribution is actually higher. It's actually fatter, thicker than the normal distribution, the assumption. For the Australian dollar, it's the other way around. For the Japanese yen, it's also the other way around, and for the British pound, it's also the other way around. So you'd be safe, relatively speaking, as far as this data set is concerned, by working with the normal, the variance covariance assumption, the normal assumption when it comes to, let's say, the Australian dollar, for the Japanese yen, and for the British pound, because your VCV estimate is actually going to be higher. This is your VCV estimate. This is your VCV estimate. Your VCV estimate is actually going to be higher. But when it comes to the euro, your VCV estimate is actually going to let you down because the actual realized historical volatility is much higher. The worst case loss is much higher. So I hope what we've done here is we've quickly calculated how to calculate value at risk estimates, very crude value at risk estimates. There are a number of refinements that we have to include in this, and we'll talk a little bit about that in the next session. But what we've really done here is that we calculated the value at risk using two separate approaches, two separate methods. The first method being variance covariance, the second method being historical simulation. We've also done a quick comparison, a quick eyeball comparison of how the four distributions for the four currencies look. We've also calculated or looked at how to read the histogram function in Excel and use that as a quick check on our estimate for the underlying value at risk estimate using historical simulation. I hope that this session was useful, you enjoyed yourself. In the next session, we look at how do we extend this process and this mathematics to commodities, and then how do we calculate value at risk for a portfolio, and how do we go about estimating the correlation, the covariance of the portfolio using a quick shortcut. Thank you very much. This is Jawad Ahmed Fareed for financetrainingcourses.com.